Um, all right, so hello everyone. Welcome to our virtual silo talk. So today we have Vivek Farias, who is from MIT. He's the Patrick J. McGovern Professor at MIT Sloan. He's very accomplished. So I won't go through his entire list of accomplishments, but to name a few, his work has been recognized with many awards, including an NSF Career Award, an MSOM Young Scholar Prize, the Wagner Prize, the Pearce Scholar Award, and was recently elected as an Informs Fellow. His papers have also won numerous prizes at Informs, and I won't list all of them here. And in addition, outside of academia, he's also a very successful entrepreneur. He has co-founded, to my knowledge, two startups, one of which was acquired by Nike and another by Salesforce. And currently, he's serving as the head of science at Salesforce Cloud. And today he will tell us about LLM alignment. So take it away, Vivek.
Yeah, thank you so much for having me. And as I mentioned a second ago, I'm sorry for not being there in person. I would have very much have liked to have been there in person, but circumstances at MIT didn't let me. In any event, as the title of the slide says, I'm going to be talking about LLM alignment in the presence of heterogeneity. I'll talk about what that means, in a second, right? But at the very outset, I'll just say that this is joint work with my colleague Ali Awad and a PhD student of ours, Ayman El Gadari. Ayman's a second-year PhD student now at MIT. A really brilliant guy, and probably deserves the lion's share of the credit for what I'm going to talk about. Okay. So just to kind of get the ball rolling, okay, so I checked that this worked, and now there we go. Okay, so just to get the ball rolling, I would like to kind of maybe set the stage. Let's do the first 3 slides roughly in English, okay? So before we get to any kind of formal setup, I'd just like to talk in English about really what this problem's about, okay? So, let's say you went to an LLM, right? And, if you focus on kind of the 2 pictures that are side by side over here, imagine that the conversation you see above the grayed out box, right? So a human says, what should I do if my boss is always mean to me? And the assistant comes back and says, I'm sorry to hear that about you, blah, blah, blah. Then the human says, he's ignorant and mean. Then the assistant says something else. And then the last sort of human input, the last human utterance is, he's mean to about half of us. I don't know what his problem is. Okay. And let's view that as the prompt, right? It's the conversation leading into something. And it's identical both left and right. All right. What is not identical are the sort of the LLM's responses. Okay. So if you look at the final response. So if you look at the final response on the left-hand side, you have a pretty sort of inquisitive kind of thoughtful response over here with the LLM saying, listen, probing more, right? What do you find bad about this? So on and so forth. And it's a longer response. And the right-hand side response is more or less saying, he's like not a good guy, right? It's just sort of like that's it, right? Like it's this 2-sentence thing which you can read. Now imagine that you showed these 2 responses to someone, right? And there's going to be random, and ask them, what do you prefer? Right? So there's going to be some randomness in their preferences, obviously. So let's say, we were able to sort of integrate away that randomness, right, for a second, right? You'll get, some preference. So maybe what you go talk to some individual, and, that individual, let's say, is described by a whole bunch of things, but here are some sort of like a short bio of that individual in that blue box on the left over there, right? Saying, where they're from and their age and this and that and the other, right? Maybe this individual comes up and says, listen, I actually prefer the first response, and I prefer it quite a bit, right? That probability of preference is 90%. Okay. Now, what you could do is you could kind of present the same task to a different individual. Okay. And really, so here we've got this different individual. They're older. They live in a different part of the country. They have a different sort of education qualification, a different education background, so on and so forth. And this person, to some extent, is ambivalent. They don't really care nearly as much about the 2 alternatives. But in fact, they have a slight preference for the second alternative. right? In this particular case. Okay. So this person says, hey, I kind of prefer, the second alternative, but just marginally so. Okay. So, what I'm showing you over here is kind of generic to the sort of inputs that you might actually get as you think about quote unquote aligning an LLM, right? Like ultimately an LLM, if all it knows is those first five utterances that you saw, needs to pick between these two alternatives. And the task of kind of figuring out, well, how do we go about that is called alignment, as everyone here probably knows already. But that alignment is informed by the sorts of inputs we saw on the last slide, right? People have diverse preferences. They're heterogeneous in their tastes, and that's where the word heterogeneity in my title actually comes from, right? Each of us has our own kind of systematic biases that inform what we might actually prefer. And those systematic biases contribute to what we will call heterogeneity. Okay, so what's the issue with this, right? So, there are many pipelines, by the way, to kind of, run alignment. And to some extent, by the way, the details of these pipelines, as we'll see in a little while, don't really matter so much. But one thing I will say is, to a large extent, practical pipelines, and I'll focus on something called RLHF, which everybody here probably knows, right? That's one way of doing alignment. It's reinforcement learning with human feedback, right? These pipelines in industry largely ignore the sort of heterogeneity I talked about. They forget about that, right? They say, yeah, there's randomness, right, in answers, but that randomness is idiosyncratic. It's not systematic, okay? And so, what does that result in? So the first thing is, people have observed over, and actually this is pretty recent, people have observed over the last like sort of year and a half, this can yield, this sort of heterogeneity can yield sort of distorted population level models. Okay, so when I learn a model of what the population prefers, there's some distortion that ignoring heterogeneity introduces. Now, one of the things I will do in this talk is I will try and characterize what that distortion is in a very simple way. Okay, understanding that distortion has been heretofore kind of a bit of a tricky task, with the general recipe being folks kind of trying to explain what an existing pipeline might do as a sort of voting rule, okay, as a sort of vote aggregating mechanism or something like that. And this is not, it's not very clear what this actually means at the end of the day. So what we'll try to do, first of all, is I'll just try to characterize what this distortion that gets introduced when you ignore heterogeneity looks like. I'm hoping that this is something, by the way, that'll be nicely self-contained. We'll all be able to kind of take away the high-level picture and perhaps even the proof, okay? Now, okay, having said all that, okay, in full generality, there's actually, we'll see again just momentarily, right, that there's no sort of way in general to learn a population level utility model from anonymized preference data. The sort of impossibility theorems that speak to kind of like, hey, you can't expect just like a general purpose algorithm to always be able to do this. Okay, and I'll allude to that in a second. That in and of itself, by the way, is a relatively fresh result from late last year. What we will do, and this is kind of the algorithmic crux of this talk, is I'll talk about how to modify a very simple, by the way, drop-in modification to existing RLHF pipelines to kind of mitigate or potentially even remove the distortion I was talking about, in the first part. Okay, so that's kind of the roadmap of the talk, right? I want to sort of first set up the problem. I want to talk about, like, if you run RLHF the way people do, what sort of distortion does this actually introduce, right? And what is that distortion in a very simple way? And then I want to transition to talking a little bit more algorithmically and speaking to how can we go about combating that distortion. Okay, so that's the rough plan of the talk. Oops. Sorry about this. That's the rough plan of the talk. That concludes my English intro. Okay, so what I would like to do next is I would like to set up things formally, mathematically, so that we can be a little bit more precise in terms of what we're doing and what we're talking about. Okay. And by the way, if there's any questions, I'm on a laptop right now, so just feel free to unmute yourself and speak up. Okay, because I can't see a full screen. I'm not ignoring you. Okay. Okay, so let me actually move on over here. I can. Okay. All right. And start with the setup. Okay. So core to the setup is going to be, depending on where you come from, a utility or a reward model. Right. So if you come from an econometric background, you might want to think of this as a utility model. If you're coming at this from a more AI-centric perspective, you might call this a reward model. And what is this sort of reward model? Like, let's set this up, right? For the purposes of this talk, right? Let's imagine we have a universe of alternatives. Okay, that universe of alternatives is script X, and think about this for our purposes over here. It's pretty easy to kind of generalize this, right? Think of these alternatives as being prompt completions. Okay, so this is all possible sort of prompt completions. That's our universe of alternatives. Okay. Now we talked about heterogeneity, and the way we'll sort of think about heterogeneity we'll say, look, there are these sort of latent users, right, which we'll sort of talk about as beta, and there's this whole universe of users which is script B. Okay, so that's the second ingredient over here. You have a user, and that user is described by this object beta in the set script B. Okay, so what's a utility function? Right? So a utility function in this context is defined for every beta. And for every beta, this utility function simply, for a given alternative, gives you a number. Okay, so that number characterizes a reward, or it characterizes how much this person values this alternative, or whatever it is. Right? And as a quick example, a quick concrete example, a linear utility function might take the form beta transpose X, for instance. Okay. The final concept I'll talk about is a random utility. Right? So this sort of points to the thing that, like, hey, at any given point in time, there's also like idiosyncratic aspects of my choice. And so in particular, the random utility for alternative X, the random utility that user beta might have for alternative X is this quantity, which is their utility, U of X beta, the object we talked about earlier, plus this random variable C X beta. Okay. And for everything we'll talk about over here, I won't make any strong assumptions on CX beta other than sort of saying it's exogenous. Okay, so basically across alternatives and users, the CX beta are essentially, IID random variables. Okay, so everything I've said so far is like 1000% standard. Okay, there's nothing particularly like this is like, there's any number of ways to kind of justify this setup. It's a very, very, very common setup. Right, nothing controversial about anything. Anything I've sort of said so far. Okay. Okay. More in that vein, right? So let's say for a quick second that the C's are sort of extreme extreme type 1 random variables, right? In that context, right? If you gave me two alternatives, let's call those two alternatives X1 and X2, right? Then for a given user beta, right, the probability that that user beta would prefer alternative 1 is simply this sort of logistic function applied to the difference in that user's utilities between the two alternatives. Okay, so again, right, like this is a standard kind of form. If you're willing to assume that C is extreme type 1, then the probability that a user prefers alternative 1 is this expression over here. It's the logistic function applied to the difference in utilities. As a side note, for everything I'm going to talk about, nothing special about me assuming extreme type 1. It just allows for this convenient functional form sigma that everyone uses. But if you replace this, you would replace the sigma with something else, and everything I talked about would sort of go through. Okay, but this just first for concreteness, it's useful to talk about it this way because this is kind of very typical to how people, the setup most people would use. Okay, so this is the probability if you got to observe beta, right? Now integrating over beta, right? Because you don't get to see beta. Beta is the person is typically latent, right? What's the probability that, a random sort of user over here would prefer alternative 1? It's simply integrating that logistic function, that previous expression I showed you over beta. Okay. So given that setup, right, what is the data we actually have? So the data we actually have may look something like this, right? So given a pair of alternatives, X1 and X2, and we can assume that we have some distribution over pairs. Again, we can be very parsimonious in what we assume about that distribution, nothing particularly deep about what we do over there, right? But given some pair of alternatives, x1 and x2, right? A user makes a choice. That user choice is a Bernoulli random variable, effectively, right? With bias given by that integrated expression I showed you on the previous slide, right? It's the integral over beta of the choice probabilities, right? So you'd see that Bernoulli choice. And a data set is simply x1, x2, y sort of tuples, right? And so that's kind of the data we'll typically have to kind of align our LLM or whatever it is. So far, I've not talked about the goal. I've not said anything about what we want to try to do, right? I've basically talked about, users and their sort of underlying utility models, that form a way that form a sort of a generative model of how these users, form their preferences between alternatives, right? I've also talked about what data might actually look like. And what you should really be kind of thinking about over here, by the way, as you sort of see this, is this sort of integral of a beta business, right? That is to say that, like, when you see a choice, right, that choice could come from any number of, there are two types of randomness over here, right? One type of randomness is the randomness in the C, right? The idiosyncratic randomness, in this quantity C x beta over here, right, in the random utility. The second type of randomness, which is more systematic, is the randomness in beta, right? That's the sort of two types of randomness you ought to be sort of focused on over here. And so I'm going to talk about what our goal is, and then I want to pause in a second for questions, okay? So this is our goal. Okay, so given this data set, and again, what was the data set? The data set was x1, x tuples of x1, x2, y, right? So given that, what's our goal? Our goal is really simple, okay? Our goal is to learn the population average utility, okay? So that is to say, I want to learn this utility function u bar, okay? And what is u bar? U bar is basically an integral of u of x beta integrated over beta, okay? So why u bar, first of all? Right? Well, it turns out that because of Harsanyi's theorem, effectively, right? It turns out that this is kind of like a legitimate way of, in fact, it's under certain assumptions, actually very weak assumptions, it's actually the only legitimate way of essentially, aggregating, cardinal preferences. Okay, so this is a very legitimate sort of thing to learn. More importantly, this is kind of what something like RLHF is implicitly trying to learn. You're trying to learn a reward function that's effectively representative, of the population. Okay, so this is going to be my estimate. This is what I'm after. Okay, I want to learn, this population average utility. Okay, and so what's known about this? Well, what's known, first of all, is that in the worst case, you can't learn U bar. Okay, so even with infinite data, right, of the type I showed you earlier, you can't hope to learn U bar. All right. What's the intuition for this? The intuition for this, roughly, okay, and it's a very simple result, by the way. It's a really beautiful result in this paper by Nika Hagtalab and Paul Goltz. And I think there's a third co-author. It's a really simple construction, but what's at the heart of this construction is, in general, it's going to be hard for an estimating algorithm to distinguish between noise introduced by the C's, right? The noise in those random utility terms, right? And the noise introduced by beta. Okay, so essentially I can always cook up problems where separating out those two different types of noise is effectively an impossible task. And when that's an impossible task, what I'm going to learn is going to be necessarily distorted. And that's kind of what these folks actually show. So in the worst case, I can't hope to learn U bar. All right, so that's one extreme of the spectrum, right? So one extreme of the spectrum is you can't hope to, in the generality of the model I just talked about on the previous slide, right? You can't hope to recover U bar. And what's important about that is, like, the model I talked about on the previous slide is, like, at some level the model, right? It's not a model I made up. This is kind of the econometric way, one would typically look at this setup. So that's one end of the spectrum, right? Worst case, you can't hope to learn U bar. The other end of the spectrum is, what do people do in practice, right? Well, what people do in practice is they kind of just ignore heterogeneity, right? So you say, well, you know what? Let's just forget about this beta business altogether, right? Let's just forget about heterogeneity altogether, and let's just simply do MLE, right? So in particular, if I'm simply doing MLE, just to kind of write down what MLE might mean, right? I'm trying to learn, u bar, okay? The variable of interest here is u tilde. I'm hoping, u bar is kind of the solution to this estimation problem, right? I'm hoping to learn u bar by basically doing logistic regression. Okay, that's more or less what something like RLHF might do. Okay, so that's the setup and the two extremes. Okay, so basically, you've got this sort of random utility model, which I kind of talked about over here, right? A world of alternatives, users beta. If I'm a user beta, I have utility u of x beta for alternative x, right? And what is the data I see? The data I see are x1, x2, choice tuples, right? So two alternatives, and nothing special about two, okay? Like could be whatever, but just for simplicity, right? So two alternatives and what somebody chose, right? So this is the pretty sort of standard generic setup over here. What we said we'd want to do is learn kind of this sort of population average utility. And what we're saying is that if I kind of think about the spectrum of kind of doing this, there are two extremes to the spectrum. On the one side, we know because of this work by Goltz et al., right, that in the worst case, you can't distinguish between idiosyncratic noise and systematic noise, right? I can create examples of data sets where even as the data set grows infinite, you can't distinguish these two types of noise, and therefore it'll turn out you can only learn a biased U bar. The other side of the spectrum is maybe we don't have to worry about this. Maybe in practice, who cares? Let's just kind of throw away the noise and data. Let's just do MLE. And, that's glorified logistic regression in this case. And, we go home. Okay. So that's kind of the setup where that's sort of, let me just pause there, to see if there's sort of questions from the room.
Yeah. So Vivek, I do have a question in here. So, why is the goal to estimate the average utility across the population? Why is it not, okay, since we are thinking about these different personas, learn it at a more granular level, maybe like a minimax objective or something on those lines?
Yeah. Good. So I think there's sort of this is what I was alluding to with Harsanyi's theorem. So basically, there's a very deep literature on this. Kirti, right? Sorry if I get your name.
Kirti, yes. Yeah.
Kirti says a very rich literature on this. So basically, right, like essentially there's sort of this question of if you have a bunch of different utilities in your population and you want to create a social welfare function that aggregates these utilities, what's an appropriate social welfare function? Right. Okay. So there's this thing called, and so one thing you could do is you could do max min, as you were sort of alluding to. You could do sum of logs. You could do any number of different things, right? It turns out though that if you know what the origin is, okay, so if you're comfortable with saying here is something that has zero utility, right? Yeah. It turns out axiomatically there's only one thing you can do, which is what I'm showing you here, and that's Harsanyi's theorem. Okay. So really any use of like these alternative things, is requires sort of an assumption which does not typically hold, in the practice of this, of doing something like this. Okay, so if you're willing to say no answer is zero utility, you kind of have to use this. Okay, you don't have much of a choice. The second answer I'll give you is less theoretical and more pragmatic. This is implicitly what is going on in RLHF, but it'll turn out, as you'll see later, and this is non-obvious. This is also implicitly what's going on in many other proposals, okay? And some of which have been proven to be extremely good. And then there's a final answer, which I will give you on when I talk about the experiments, which is that the max-min approaches don't work well in practice, okay? Okay. So there's three ways of answering it. Great question.
Okay. All right. Okay.
Other questions from the audience?
Yeah, I have a question, Vivek. This is Ramya here.
Ramya.
So, I was curious about the result on learning U bar being not possible.
Yes.
Is it related to also if I was interested in just the average win rate? Like I look at the predicting the preference using the utility that I have learned. So there is a U bar, and if I wanted to predict on average what is preferred versus instead of saying I want to learn the U bar itself, but if I was looking at
that you can obviously do with infinite data, right?
Yeah.
So that you can of course do.
So this is more about identifying specifically what the U bar is and not just predicting using it.
That's correct. But you'll notice that that's actually a very important task in these domains. So the reason people care very, so you may ask, so there's a deeper question you could ask here, right? Which is why bother about learning U bar, right? That's the implicit question, right?
Yeah.
Why would one even bother about learning U bar? And there's a very pragmatic reason for that. It's actually about generalizing out of distribution. So effectively, if you sort of think about how these things are captured, right? You're actually going to predict preferences on like some training data set, right? But then you kind of want you want to actually use these models on things that may not even be actually not may not almost always are not actually from the same distribution, right? And so in order to be able to do that, right, you need to kind of understand, well, what is the utility model, right? And this is actually like when people train reward functions in practice, right? This is actually a very common thing that they care about. So they care very, very deeply about how is the model going to behave in some yet unseen situation. And that's why people care very deeply about recovering the use.
Thank you.
Yeah, good question. Great question. Okay. Any other questions, guys? Okay, good.
This is Shinji. I want to ask a quick question.
Okay.
When you're trying to learn this U-bar using the persona here, do you have any assumption about the persona distribution?
Well, I've
And
not talked about any of that yet, Jinji.
okay,
So why don't we wait to get there, right? Like I think what we have said so far is that learning that U bar in generality is impossible. And the second thing I've said that is in practice, people just don't even try modeling that mixture over betas because it's just too hard to do,
okay,
right?
okay.
This is very, very hard to do. So in practice, people don't even try doing that,
Mhm.
right? It's just very brittle.
Oh,
And so, but we'll talk more carefully about that.
sure.
Okay. All right. So the first thing I want to ask, okay, is maybe we shouldn't care about this, right? So maybe like just do MLE and go home and you'll be happy, right? Like, sure, right? Like maybe like people are doing it. Maybe the distortion's like actually only in these worst case situations, right? Maybe we shouldn't worry about it at all. So I want to give you to do two things. So first, I want to start with like a simple toy example to give you a sense of what can go wrong with MLE. But then I'm going to sort of talk about, well, maybe this is not just a toy example. Maybe actually the bias we're talking about over here is something like there's something truly systematic that happens that we should worry about, okay? And so let's start with the toy example, okay? So here's the toy example, and this is the toy example from the first slide, right? Basically, I have kind of these two personas, the blue persona and the green persona, and the blue persona prefers the first alternative, right? This is the answer that was more thoughtful and so on and so forth, with probability 90%. And 10% of my population is the blue persona, okay? So 10% of my population is the blue persona. That 10% of the population has a strong preference for the first answer, okay? So that's the thing at the top. And then 90% of my population is the green persona. And this green persona is sort of insensitive to a first order between these two alternatives, but has a mild preference for the second alternative. Okay, so they prefer the second alternative with probably 55%. All right? So this is, let's say, the setup and the mix, right? So what would happen over here? So first off, in this very simple world, right, I can just calculate from this data, right, that the difference in the utilities between option 1 and option 2 as implied by this 0.9, the difference in utilities is 2.2. Okay? And this essentially, remember we said the C is like extreme value type 1, right? So that's really what's behind calibrating the 2.2. Okay? And for the second group over here, right, doing that same thing, right, the difference in utilities is negative 0.2. Right? And that's as expected. The first group strongly prefers the first alternative, so it makes sense that the difference in utilities is large. For the second group, relatively insensitive. And so slight preference for 2, the difference of utilities is small but negative. Okay, so in this setup, let's try and see what happens if we did 1 MLE and 2 if we just kind of aggregated utilities, right? So sorry, my screen is kind of behaving poorly here. Oops. Sorry about that. Sorry, I'm struggling with some. There we go. Okay, so if I just aggregated these two utilities, right? So that's like basically 0.1 times the first utility difference plus 0.9 times the second utility difference. The population average in utilities is 0.04. So the population actually prefers the first alternative, right? That's kind of what would happen over here. On the other hand, if I did MLE, right, what would MLE do? It would just match probabilities, right? And if you did MLE and you just match probabilities, MLE would actually switch preferences. Okay, so in particular, what MLE would do, what you'd get out of MLE, right, is a difference in utilities that's negative 0.02. So this is sort of something where, right, again, if the population average would prefer the first option, but MLE would actually switch these preferences. Okay, so now you might look at this and say, well, this is like some toy example, right? What do we sort of take away from this? And indeed, that was sort of my reaction as I was kind of playing around with these examples. So what I'd like to do is kind of say, okay, is this like just some random example, right? Where MLE kind of switches preferences and like, whatever, and we don't really care about it? Or is there something, deeper going on over here? Okay. So I'd want to give you guys a sense of that is indeed something deeper going on over here. Okay. And to do this, I'm going to kind of consider a very simple, a more general, but relatively simple setup to kind of explain what MLE does, okay, in the presence of heterogeneity. Okay. So for my argument, right, for this sort of, mental sort of model of what MLE does, let's imagine that the utility function is linear. Okay. So U of x beta is beta transpose x, right? And let's assume that these alternatives, right, x1 and x2, let's say they're high dimensional, but the difference is distributed as Gaussian. Okay, so the difference in x1 and x2, it's sort of multivariate. It's a multivariate Gaussian. Okay. Here's actually what we can show. Okay. And I want to sort of explain why this result is important or interesting from a sort of mental model perspective first. And then I'd actually like to show you a proof because the proof is actually really, really cute. Okay. So really, here's what we can say. All right. So if you did MLE, the MLE estimator is biased, like no surprise, right? But we can characterize what that bias actually is. Okay. So if you look at this expression over here and you forgot about that intermediate term, right? What we can say is that beta RLHF or beta MLE, right? That's proportional to a weighted expectation of beta, okay? So now what would we like ideally? What we want ideally is that W of beta is a constant, right? We want W of beta to be a constant ideally, right? That's what we would actually like. But it turns out that W of beta is not a constant, all right? In particular, W of beta is such that basically for large beta, W of beta is really, really small. Okay. So let me just say that again, right? If we did MLE in this context, MLE would learn this weird weighted average over betas. Okay. Now, ideally, we want that weight to be uniform. We want that to be a constant because we want literally the expected value of beta. That's our goal in this context, right? But it turns out that when you do MLE, that's not what you get. Instead, the W of beta is such that it discounts large beta. W of beta grows small as beta grows large. And what does that mean? What that means is the following, right? Beta being large, okay, is basically folks that have low variance choices. Okay, beta being large is basically, these are folks that are very confident of their answer. Okay, that's what beta being large is. And what MLE does in this context is it essentially de-weights the choices of confident inputs. Okay, that's basically what's actually going on over here. And if you kind of come back to what you were seeing in this example, that is actually what happened in this example, right? The first guy at the top was super confident, had a very strong preference. The second person had a very weak preference. And effectively what ended up happening is that strong preference effectively got de-weighted some. And in fact, in this context, it got de-weighted enough that the population preference is estimated by the true population utility vis-a-vis MLE essentially switched. What this is saying is that may actually be a more general sort of thing over here, right? That is to say, in this simple setup, RLHF will sort of heavily discount strong opinions. Okay. How do we go about seeing stuff?
Vivek, I have a question. This is very interesting, but I was trying to kind of reconcile this with the setting where like usually it's difficult to we know that like when you have like the Bradley-Terry model, utility is something that we can only learn up to scale, right? Like because it's you get the same comparison because we only have comparison data. So usually what we tend to do is to learn the utility with
But that's exactly what's happening here, right?
yeah,
You'll only learn it up to scale.
Yeah, so but like usually it is done by constraining the norm of beta. Like even when we
but you can't. No. You can't constrain the norm of beta to be unit norm, right? You can't do that, right? That's a much stronger restriction. You wouldn't be able to get like the same utility across all alternatives then, right? So what we're talking about over here is basically, so good. So if you sort of think about what's actually happening in this particular setup, right? In the Bradley-Terry model, right? There's sort of like invariance essentially to sort of multiplicative choices if you don't know variance, right? That's fine for what I'm saying over here, right? Notice that this result is just talking about something that's proportional to, right? So irrespective, you would want that W of beta over there to be a constant.
Mm-hmm.
You see what I'm saying? And so one way of kind of thinking about how does that W of beta behave? Yeah, I mean, up to kind of whatever the scale term is, you'll still get that same behavior.
I see.
So you see what I'm saying?
So maybe then to reconcile in the setup, because usually like even when we are trying to, in the settings where we do have, anonymized IDs and you're trying to, let's say, learn the latent vector beta, usually the way it's done is to have a constraint on how large, like usually you can.
You can do that. Just to be clear though, if you restrict all betas to be on like the unit ball, that is a restriction.
Yeah.
Right. And that's a very strong restriction if you did that. Right. Like, so you'd essentially be a priori limiting heterogeneity by doing something like that.
Yeah.
So I think what you can do is do invariance
like you're putting it to the unit sphere, like not just on the not equal to unit norm. Usually it's put it, think of it as like less than or equal to 1.
Yeah.
So the predictions still will be the same, right? Like, because usually when I'm predicting in Bradley-Terry model, I'm only looking at the
actually, that's a good question. So actually, it turns out that if you ignore the heterogeneity in betas, it's unclear that you're going to get perfect predictions either, right? Because your model class won't be rich enough.
Yeah.
Okay.
Yeah, I'll also like ask few other questions offline, but this is super interesting. Thanks.
Okay. So let's actually, and the proof might be actually illuminating, by the way, of what's going on, right? So here's one way of thinking about it, okay? And this is, by the way, the only reason I did normal, because I can use this sort of Stein's identity to kind of characterize a normal, okay? So here's what we're going to say, right? Like I'm going to basically, to talk about this bias result, I'm going to use Stein's identity. So Stein's identity, just as a refresher, this is a characterization of the normal distribution, okay? So in particular, if you had a multivariate normal and you had any sufficiently nicely behaved, I think you basically need it to be absolutely continuous, any sufficiently nicely behaved function G from RD, D is the dimension of this normal, right? So high dimensional sort of, alternative vector, whatever you want to call it, right? So if you have any sufficiently nicely behaved function, like really absolutely continuous, right? Then Stein's identity says that really, right, these two, you have this nice expectation relationship. So the expected value of x times g of x, right? And remember, x is a vector, g of x is a scalar. The expected value of x times g of x is the same as the expected value of the gradient of g, okay? So that's Stein's identity, and this is actually a way to characterize actually normal distributions. Now I'm going to kind of turn that around and use that, in our context, right? So let's say we did MLE, and we did MLE just ignoring the heterogeneity in beta. So that's wrong, right? It's like an ill-specified MLE, but let's say we did that. Right? So we did that. What's our moment equation? Our moment equation that identifies, beta RLHF or beta MLE is kind of what I've written here. It's the moment equation for logistic regression, right? Essentially what you're saying is that you want to kind of moment match between what your model predicts and what you actually observed, right? So on the left-hand side, you've got, the expected value of x times the probability that one, that the user chooses the first alternative. On the right-hand side, you've got, the product of x and sort of the observed kind of choice, right? And what MLE will try to do is it'll use this as kind of an identifying equation, right? Now, what we can do over here is we can apply Stein to both sides, right? So on the left-hand side, I can apply Stein treating sigma as G, right? And what you get out of that, is the quantity that you sort of see over here, right? It's some constant that depends only on the distribution of X and your estimate, and your estimate, beta hat. On the right-hand side, I'm going to apply Stein to this conditional expectation of Y given X, right? And what you see popping out of this is the result at the top, which is to say that a given beta is weighted by the variance of choices at that beta, okay? Now, by the way, you will notice that in what I actually did over here, I actually made no assumptions on the distribution of beta. So this comes back to Ramya's question, right? So if you wanted, you can do whatever you want to beta, right? There's nothing deep, nothing special that I've assumed about beta over here, right? Other than assuming some nice real analysis stuff for absolute continuity, right? But so what we're seeing is that irrespective, right, the weighting that you're going to get is this weighting that basically weights a given beta by the variance of choices at that beta, okay? And so let's say, like Ramya was saying earlier, you decided to restrict beta to be in some set, whatever that set is. To the extent that there's kind of high variance betas in terms of choices and low variance betas in terms of choices, right? You're going to weight a given beta by that variance. And so put another way, right? In your population, folks that are confident of their answers, right? Like, so you can imagine, right? Like that, like basically, for a given question, there's polarization, and one group cares very deeply about one answer, very deeply about another answer. And then there's a third group, maybe that's somewhere in between, right? These extreme choices are going to get deweighted. That may be viewed as almost a positive thing, by the way, right? A different way of looking at it that's not positive is imagine that low variance indicates confidence in an answer, right? So I'm sure last week, a lot of you were, replying, or maybe we're still replying to your ICML submissions, right? Essentially, what something like MLE would do in this context is it would basically say, if there are people that have confidence in their answer, we're going to deweight all of those, right? And equivalently upweight the people that actually have low confidence. And so that's kind of what's going on when you do MLE. Okay, so when you do MLE, you end up deweighting low confidence answers, equivalently upweighting, you end up deweighting high confidence answers, equivalently upweighting low confidence answers, and that's bad, okay? So we've kind of gone through the first piece over here, right? And what we've said is that, and by the way, if you leave with nothing but this, I'll be actually happy, right? Like, hopefully you'll leave with a nice mental model of what ignoring heterogeneity does when you try to learn a reward model. And what you should be taking away from this is when you ignore heterogeneity, you end up learning this bias, this weighted average over betas, and the weighting basically is small on high confidence, on low variance betas. Okay? And that's not something that's necessarily a good thing. Okay? All right. So what I want to do is maybe speed up a tiny bit. Okay? And I want to talk about how we might actually go about addressing this. Okay? Can we do something that maybe mitigates this distortion somewhat? Okay? And here's what I'd like to do. Okay? So as I already said, right, in general, we can't learn U-bar, right? That's not something we can do in general. So here's my plan. Okay? So what I'm going to do is I'm going to make an assumption. Okay? It turns out, by the way, this assumption is weaker than sort of the typical assumption made when folks model heterogeneity in econometrics. Okay? It's actually much weaker, right? But nonetheless, it's going to be a structural assumption. And so first, I'm going to talk about what that structural assumption is. It turns out it's a very old structural assumption. I'll be able to relate it to some pretty old work. The upshot of this assumption is it's going to give us a drop-in replacement for the use of cross-entropy, or effectively MLE, when you do RLHF. Okay, I'll give you a simple drop-in replacement. All right, and we'll see how we get that. And then I'm going to show you that this actually, show you some results and show you that in practice, this actually works pretty well. Okay, so let's get started with that second piece. And let's actually talk about, I'm going to walk towards my structural assumption. Okay, so to do that, first I want to define something, okay? So I'm going to basically say that if you give me a scalar random variable epsilon that has a density, okay, so if you give me, so an atomless distribution, okay? So if you give me an atomless epsilon that has a density, I'm going to say that it has zero median, right? If the probability that epsilon exceeds zero, that epsilon strictly greater than zero is a half. Okay, so that's what I'm going to say a zero median random variable actually is. Okay, so now here's the assumption I would like to make. Okay, so consider let's define epsilon of x. Okay, as sort of the difference between the utility that a random user beta has with the mean utility u bar. Okay, so let's call u of x beta minus u bar of x, let's call that epsilon of x. And you can kind of think about that random variable as capturing sort of the heterogeneity in utility for alternative x, right? And we're mean centering this. So epsilon x is, of course, zero mean by definition of u bar. Okay, so by definition of u bar, epsilon x is zero mean. Here's the assumption I'm going to make. I'm going to require that for any two alternatives, okay, you give me any two arbitrary alternatives, I'm going to require that epsilon x1 minus epsilon x2 has zero median. Okay, so now let's just try and understand what that's saying, right? So first of all, epsilon x1 and epsilon x2, right? These are independent zero mean random variables, right? So epsilon x1 and epsilon x2 has zero mean. In addition, I'm asking that it has zero median. So the question becomes, okay, bit of a, what does this actually mean, right? Like, can we relate this to other assumptions people make? So let me say two things over here. So first of all, right, in practice, in practical sort of modeling of heterogeneity, right, at least in linear models, for instance, one will often model the distribution of beta as some sort of multivariate Gaussian. This is the most common kind of modeling technique, in linear high dimensional models. If the distribution of a betas is a multivariate Gaussian, then that actually makes epsilon x1 minus epsilon x2 symmetric. Okay, so even stronger than zero median. So in particular, one thing over here, okay, is that essentially any sort of typical heterogeneity setup that you see in econometrics automatically satisfies this sort of zero median condition. But nonetheless, it's an assumption, okay? And in fact, what we'll see is that, like, in practice, you can't really expect for this assumption to hold, but nonetheless, it's actually going to give us algorithms that are much more robust than the use of MLE, okay? So, by the way, where was this assumption originally introduced? This assumption was originally introduced by Charles Manski, okay, in 1975. I didn't invent this assumption, right? So it's a 50-odd-year-old assumption. And it was actually invented in the context of, robust estimation, right? So Manski was sort of unhappy with, like, the general sort of flow of, like, how people model robustness, modeled heterogeneity, and said, well, these are, having these sort of symmetry assumptions is too strong. Can we do something weaker? Okay, so the assumption was originally made, quite some time ago. Okay.
Vivek, just
Yeah.
to and better understand the condition. So is it just saying for any two alternatives, there is a winner, in the sense it's not going to be no winner situation would be the the difference probability of that distance. I'm just trying to understand, like, what does it translate to kind of more intuitively, like?
Yeah, so I think intuitively, I'd like you to think about it slightly differently. So intuitively, this is how here's one nice intuitive way of thinking about it. So one nice intuitive way of thinking about it is as follows, okay? And this is strong, this is implied, it's not necessary, okay? So imagine that, right, for a given alternative x, you drew a histogram of, ux minus its mean, right? What this is saying is that histogram looks symmetric around its mean. Okay, so it's basically saying that, like, right, that's the mental model of how you want to think about this. Okay, so that's how I would actually think about it. But it turns out that you can get away with something much weaker. It doesn't have to be symmetric. All you need is that the median and the mean coincide. Okay, so that's basically what it's saying. So in particular, by the way, right, if that distribution has very high kurtosis, that's not good equivalently. Okay. All right, so very high kurtosis is probably bad. All right, that's far away from this assumption. Make sense?
Okay, yeah, thank you.
Yeah, okay, good. So here's why this assumption is even interesting to begin with, okay? So here's the story, all right? So basically, if that epsilon has zero mean, okay, it turns out that you get a very nice identification condition for U bar, all right? And this is like this is pretty cool. Here's the identification condition, right? The identification condition says that the sign, okay, of choices, right? So this relates to Ramia's thing, okay, which is basically, do people prefer one or the other, right? Like when I look at integrate over the whole population, right? Is there a preference for the first one or the second one, right? That sign has to then agree with the sign of the difference in the U bars. Okay. Now notice that in this identifying condition, there's nothing about the model of, nothing about like, I don't have to model anything about the mixture of betas, right? That distribution over betas or any of its moments, they don't enter this condition at all. All right. And so what this says is, hey, if you had this zero median condition, you can identify the sign of the difference between the mean utility for any two alternatives. I'm going to skip the proof of this. The proof is actually very pretty, but in the interest of time, I'm going to skip the proof of this fact and simply get to kind of what this lets us do. Okay. So given this identification condition, okay, and I'll prove what this identification condition buys us in a second. Actually, yeah, okay, I'll prove what it buys us in a second. This identification condition motivates a different estimator than MLE, okay? What is this estimator? This estimator is saying simply try to align the signs of the choices, okay? So think of this as 0-1 classification, okay? What this is basically saying is, hey, actually, let's say instead of MLE, the logistic loss function, you did 0-1 classification, 0-1 loss, okay? It turns out that 0-1 loss, okay, is the estimator aligned to this identification condition. What do I mean by this? What I mean by this is the following result, okay? If you actually solve this 0-1 identification problem, right, you're not going to recover U bar, but you will actually recover an ordinally consistent version of U bar. That is to say, for any two preferences, X1 and X2, in the support of script X, right? Your estimator, U bar, will prefer things correctly compared to the true population average. This is not something you would get with MLE. If you think about this in terms of like the special case where you're recovering the beta vector itself, the mean of beta, you of course can't recover the scale of the mean of beta, right? That's obviously impossible. But what this says is that you will recover the vector up to normalization, up to a single sort of scaling multiple exactly, okay? So that's a lot to take in, but let me just say this again, okay? And this is kind of the simple takeaway I want you to kind of sort of take from here, all right? Oops. Where was this? Sorry, yeah. This is the simple takeaway I want you to take from here, okay? So look at the second equation display and the third equation display on this slide, okay? The third equation display, the one at the very bottom of the screen, is MLE. Okay, that's MLE. This is like the logistic regression thing, right? And what did we say about MLE? We said MLE is kind of screwy over here. It basically takes confident sort of things and discounts those confident preferences, right? The option at the top is what we're suggesting as a drop-in replacement for MLE. That drop-in replacement basically replaces MLE, essentially this cross-entropy loss, okay, with the 0-1 loss. In practice, it'll turn out that we don't want to do exactly the 0-1 loss. Instead, we want to take that sign and replace that sign function with kind of a temperature and yield version of that sign function. Okay, that's the practical thing, and we'll talk about why that is in a quick second. It turns out that if you did that, the expression at the top looks very similar to something called Salas entropy. Okay, and so basically the idea over here is that if you have, and this is kind of the one sentence, if you have heterogeneity in the population, you want to replace the cross-entropy loss with the Salas entropy loss, okay? And why would you want to do that? You'd want to do that because at the very least, doing Salas entropy gives you robustness up to this sort of zero median condition, okay? All right, so we're running out of time. And so in the interest of time, I want to sort of skip a whole bunch of things that I think I was a little bit optimistic in terms of what I would cover, right? I will say, by the way, as an advertisement for the paper, that we've proved some very, very nice pretty non-trivial results about recovery rates and so on and so forth. If you enjoy this kind of thing, you'll kind of like this, and I'll point you at the paper, right? But what I'd like to do in the interest of time is actually talk about how does this work in practice, okay? So I'd like to kind of spend the last couple of minutes just talking about how well this works in practice. Okay. And to that end, right, I'm going to look at three in a second, open source data sets that some of you have probably seen. One is sort of the Anthropic helpfulness data set. And this is sort of, 44 sort of alternatives, 44,000, alternatives with human choices. The other is the Stanford SHP data set. That's a slightly bigger data set, okay? And in reward model training, these are data sets that people commonly actually look at. Now, to begin with, you can simply consider predicting the true labels on these data sets, right? But you just consider that prediction task. Okay, there's not, to be clear, we want more than that, right? But let's just start with what a lot of people do, which is predicting labels. And let's see what actually happens over there. So when you try and predict labels over there, by the way, the thing that I'm calling EM is kind of this max-min algorithm that was kind of proposed last year for this heterogeneity thing. Okay, I'm calling it EM because ultimately it is EM, all right? And it has sort of effectively a single hyperparameter. All right. So I'm going to compare this RLHF along with this sort of sign estimator, this Solis entropy kind of loss that I was sort of talking about earlier. And you can kind of see that, like, yes, it does better, right? But there's actually more than this. So very recently, in the order of like maybe 2 months ago, OpenAI released something called the Coval data set. And the Coval data set is a very, they're pretty exotic things that people are asked to compare between in that data set. So the first thing, if you see that third line over there, again, this sort of Solis entropy is better than all these alternatives. But what I find particularly interesting, and this speaks to a point we asked earlier, right? We ultimately care about recovering the reward model. So if you actually went ahead and trained, on let's say the HH data set, but then you evaluated on the Coval data set, what you'll see is that the loss in performance for the sign estimator, the Solis entropy estimator, is substantially smaller than the other alternatives, okay? So this sort of suggests that out of distribution, as we would expect, right, this sort of generalizes better. That said, this is still less interesting because why predicting labels is not equivalent to me maximizing utility, and it doesn't really test recovery of the utility model itself. So to test that, and I'm going to say this for 1 minute and then I'll end, what we did is, we went and we took the helpfulness, the HH data set, and then we took, these 2,000 odd personas that are effectively 2-hour-long interviews with individuals. Okay, so this way we've got the individual in a box, and we've got this long persona, right? And we'd say, hey, pretend that you're this person, right? 2 hours of like talking. How would you then respond to this question, right? Now, the power of doing this is you can actually recover ground truth individual level utility models. Right? And having recovered ground truth individual level utility models, you can test how much better do you do at actually recovering this sort of estimate, right? So basically, right, I essentially take the helpfulness harmless data set, I run every persona against it, against the 64,000 or 44,000 odd questions, and I'm able to recover persona level utility functions by doing this. I'm going to skip this and sort of just end with kind of like the upshot of all of this, right? When I look at this now, right, I've actually got a ground truth utility to compare against, what you actually see in this context, okay, is that both in terms of recovering the actual utility model, so this is the angle over here, right, because that's the meaningful thing to capture, and also in terms of decisions, right, the utility loss in terms of the true sort of utility, there's a substantive kind of decrease, or rather increase in performance relative to RLHF. Okay, so that's kind of what I had for you. What did we actually show here, right? We showed two things. Okay, the first thing was if you just ignore heterogeneity, you incur distortion, and that distortion takes a very specific form. Okay, you end up discounting confident opinions or strong opinions. Two, we showed a nice drop-in replacement for cross-entropy that has very, very nice properties. One, it sort of seems to empirically perform really well. But two, it actually has these nice properties in terms of the ability to actually genuinely recover U-bar. Let me actually stop there. I think I'm 2 or 3 minutes over time. I apologize for that. But yeah.
All right, thanks, Vivek, for that interesting talk. I think we have, we are over time, but maybe we could have time for me one question just to wrap up. Yeah, so Vivek, so maybe I could ask something. This is less to do with your talk, but it's more to do with like the general space itself. So it seems like the key challenge here is that you're trying to elicit this binary feedback, right? Do you prefer one over the other? And has there been any work either by yourself or others on looking at other forms of feedback in order to maybe learn this more? Um,
Yeah,
yeah.
so there's nothing specific about binary over here.
Okay.
So everything I'm talking about would work for anything ordinal.
Okay,
right?
right. It's a comparison, right? Yes, it's a
Yeah, but
comparison as
that
opposed
at
to
some level, that's kind of what you have,
right.
right,
Okay.
in
Yeah.
practice.
Yeah.
Now, you could imagine other types of feedback, I guess, which is like you could ask people to give you like long form answers, right? You could ask somebody to sort of say, hey, why did you do this? And, so on and so forth. And I think that's actually a very interesting direction for work. Like it's unclear how to formalize that, right? Because, at some level, we've never really been able to contemplate that type of feedback in the past, right? At scale.
Yeah.
But here, maybe you can actually get people to kind of explain their reasoning, and that would be a different type of feedback. But I'm not aware of any very much research on that type of feedback. But to me, at least, that would seem like a very natural way of kind of expanding the type of feedback you get beyond ordinal.
Okay, sounds good. All right, thanks for that nice talk, Vivek, and let's give a virtual round of applause to Vivek. And there you go.
Yeah, thanks everyone. I'll see some of you in our one-on-ones.
One-on-ones. Okay, all right.
Take care. Bye.